So prior to the ideal gas law, we had three predecessor laws: Boyle's law, Gay-Lussac's law, and Avogadro's law. Now, I'm personally not an advocate of really learning these laws, but they are part of the curriculum, so I will begrudgingly tell you that you do need to learn them. However, the ideal gas law is one of those laws that we have it for a reason, and it's easy to backtrack the three laws from the ideal gas law. But let's start simple. Prior to the development of the ideal gas law, we had three leading gas laws that were used to describe properties of ideal gases. The first is going to be Boyle's law. So Boyle's law says that pressure and volume are inversely related. So a way to think about that is if we take a cylinder of gas at a given pressure and we make it smaller volumes, we're going to end up driving up the pressure. So Boyle's law says that for constant moles of gas and constant temperature, pressure times volume is equal to some constant, and we're just going to identify here as K1. So this is your Boyle's law expression. Second law that came out during the development of these laws is the Gay-Lussac's law. Now, Gay-Lussac's law says that temperature and volume are proportional to each other, with temperature being an absolute temperature. You'd be working Kelvin or Rankine if you're really back in those days. So the way to think about this is if we have a balloon with a constant pressure being acted on it and a constant moles of gas inside the volume, we take this balloon from a hot room to a cold room, what does the volume of the balloon do? Well, it goes down. And so we got our second relationship, volume equals some constant times temperature. And this is your Gay-Lussac's law. Now, the final law is Avogadro's law. Now, you're going to remember Avogadro back from moles to mass conversion. So Avogadro here is going to deal with moles, specifically moles and volume. So the way to look at Avogadro's law is to say, okay, if I take a volume of a balloon, if I take a balloon with a given volume and moles of gas in it and I add gas to it at a constant temperature and pressure, what do I expect the volume to do? And as you expect the volume to go up as the moles of gas increase. So we have our final relationship, V equals moles times some other constant K3. Now you can see the hintings of the ideal gas law here. PV equals nRT with our constants K1, K2, and K3 representing the variables that we're holding constant. So how do we practically use these laws? Well, first thing we have to do is look at any given problem and say what's being held constant. So if pressure and volume are varying, but moles and temperature being constant, we're dealing with Boyle's law. If we're holding pressure and moles constant, we're dealing with Gay-Lussac's law. And if we're holding temperature and pressure constant, we're working with Avogadro's law. So how do we work with them in terms of getting numbers? Well, let's say you're given a problem. And the given problem says that we're dealing with a gas with a 2-liter volume and 101.325 kilopascals of pressure. And at constant temperature and constant moles, we decrease the volume from 2 liters to 0.5 liters. What's the new pressure? Well, to answer questions like this using these gas laws, the first thing you need to ask yourself is what's being held constant or what's being changed. So the problem I just gave you, I'm changing pressure and volume. So in this case, I'll be working with Boyle's law. So I don't need to worry about these other two laws. Now I need to identify what the change is. So in this example, the starting pressure is 101.325 kPa. Starting volume is 2 liters, and the final volume is a half liter. And I'm being asked, what is the final pressure, P2? Well, off the bat, you should know that your units have to stay constant, so our final answer here is going to be in kPa. Now, there's two ways we can use Boyle's law or Gay-Lussac's law or Avogadro's law. One is we can solve for this unknown K1, and this K1 is going to contain everything that's being held constant plus the ideal gas constant. So in this case, we could say, well, I know pressure 1 and volume 1, that has to equal K1. So 101.325 times 2 is 202.650. And now if I want to know pressure 2, all I have to do is say, well, pressure 2 times 0.5 equals 202.650. Well, I just have to double that to get rid of it. So pressure 2 is 405.300 kPa. I'm really hoping that's right. Second option. So what option? Solve for the unknown constant and then use that proportionality constant. The second option is to take the ratios. So I have P1, V1 equals K1, and I also have P2, V2 also equals my constant K1. So if I just take the ratio of these two equations, my K1s are going to cancel out. So I get P1V1 over P2V2 equals 1, or if I rearrange the equation, P2 equals P1V1 over V2. So just plugging in these numbers, I can backtrack out the pressures. So there is still some utility associated with these old gas laws in the sense that if you're given two of the variables and the ones being constant, either one, you can solve for the proportionality constant that's in the equations, or two, just take the ratios. And in using the ratios, you should be able to backtrack out the exact same answer as if you found the K1. So this is working with and understanding basically these predecessor gas laws: Boyle's law, Avogadro's law, and Gay-Lussac's law.